Good morning, everyone. I am Desta Tatel, and I am pleased to welcome you all today. We will be exploring the fascinating ways physics applies to various other fields. Today's presentation is titled Grade 12 Unit 1, Application of Physics in Other Fields. We'll look at how physics principles are used beyond the classroom, impacting different industries and everyday life. I hope you find this session both informative and engaging. Let's get started. Physics provides us with fundamental knowledge that is essential across various branches of engineering. Think of physical concepts like mechanics, thermodynamics, electromagnetism, atomic physics, molecular physics, optics, and nuclear physics. These are not just abstract ideas, they serve as vital inputs when working in different engineering fields. For example, civil engineering relies on understanding forces and material behaviors, which are rooted in mechanics. Mechanical engineers need thermodynamics for engines and energy systems. Electrical engineers work with electromagnetism to develop circuits and devices. These physical laws and principles form the backbone of engineering solutions. In fact, many engineering problems are complex and difficult to solve without a solid understanding of physics. When we grasp the laws of nature through physics, we gain the ability to predict outcomes. This prediction capability is crucial when designing and building things, whether it's a bridge, a machine, or an electronic device. So, understanding physics isn't just academic. It's a practical tool that helps us foresee what will happen to the structures and systems we create. It allows us to make smarter, more reliable engineering decisions, ensuring safety and efficiency in our work. Civil engineering is all about designing and building some of the most impressive structures around us, like skyscrapers, roads, bridges, dams, and railways. And to do this, we rely heavily on our understanding of physics, forces, fluid pressure, gravity, and many other concepts. These principles help ensure that our structures are safe, functional, and durable. Historically, civil engineering has been around since ancient times. Civilizations like those in Ethiopia and Egypt built incredible structures, temples, pyramids, and palaces, long before modern engineering tools. These early engineers used their knowledge and intuition to create lasting monuments. However, the major breakthroughs in civil engineering really took off with the development of physics, especially after the 18th century. The laws of motion, the concepts of power and energy, these fundamental ideas transformed how engineers approached construction. They allowed for more precise calculations and better understanding of how structures behave under different forces. Today, thanks to advances in measurement accuracy and computational methods, we can design and build incredibly complex structures, skyscrapers that reach for the sky, advanced transportation systems, suspension bridges that span great distances, all around the world. These innovations continue to push the boundaries of what's possible in civil engineering. Mechanical engineering relies heavily on our understanding of mathematics and science, especially physics and materials science, to design and create various mechanical systems. These include engines, manufacturing equipment, and vehicles. When we talk about physics concepts like mechanics, which deals with motion and forces, or thermodynamics, which involves heat and energy transfer, we're applying these principles directly to real-world applications. In mechanical engineering, concepts such as forces, stresses, and aerodynamics are crucial. For example, when designing an aircraft or a watercraft, understanding how air or water flows around the structure is vital. Similarly, in building engines or robotics, we need to ensure that these systems can operate efficiently and safely. The goal for a mechanical engineer is to take one or more of these physics concepts and develop a mechanical system that functions reliably without failure. This involves careful analysis and application of these principles to ensure durability and performance. Ultimately, all these efforts aim to improve how we create and optimize machines that serve various industries and everyday life. Electrical engineering is all about designing a wide range of electrical circuits. These include motors, electronic appliances, optical fiber networks, computers, and communication links. It's a field that touches many aspects of our daily lives and technology. Often, electrical engineers need to convert electrical energy into other forms of energy, like mechanical energy, which powers machines, or thermal energy, which we use in heating systems. This conversion process is a fundamental part of what electrical engineering involves. Because of this, a good understanding of certain physics concepts is essential. Concepts like electromagnetism, which explains how electric and magnetic fields interact, mechanics for understanding motion and forces, and thermodynamics for energy transfer and heat, are all crucial. These physics principles help us design efficient systems and solve real-world engineering problems. So, in summary, electrical engineering isn't just about circuits. It's a multidisciplinary field that combines electrical design with core physics concepts to create the technologies that power modern life. Chemical engineering is all about producing products through chemical processes. This involves designing the equipment, systems, and processes needed to refine raw materials and to mix, compound, and process chemicals effectively. At its core, chemical engineering relies heavily on the laws of physical chemistry and physics, which help us understand whether these operations are practical and efficient. A key point to remember is that understanding the physical properties of molecules and the chemical bonds between atoms is crucial. Molecular physics helps us delve into how molecules behave and interact, which directly impacts how we design and optimize these processes. Additionally, the concept of energy changes, which comes from thermodynamics, plays a vital role. Knowing how energy is transferred or transformed during these reactions helps us improve efficiency and control over chemical processes. So, in essence, chemical engineering is a blend of understanding molecular behavior, energy dynamics, and applying physical laws to produce useful products safely and efficiently. There is a fundamental connection between physics and technology. Without knowledge of physics, most of the technologies we know well today could not be available for society. Dear students, do you think the reverse is also true? Can technology give rise to new physics? Science and technology are two things that are completely interwoven. Science seeks to understand the natural world using technology. Engineering, on the other hand, uses scientific discoveries to design products and processes that solve societal problems. So, technology doesn't just rely on physics, it can also help us discover new physical principles. This mutual relationship highlights how advancing one can lead to breakthroughs in the other, driving progress forward. These products and processes are what we call technology, and they're really important not just for scientists, but also for engineers. You see, technology wouldn't exist without science, because science provides the fundamental knowledge, and without that, technology wouldn't be able to develop. On the other hand, science becomes much more effective and gets a boost from the technology that we create. Think about it, the technology developed through scientific understanding allows us to do even more science. Many of the modern experiments we rely on today simply wouldn't be possible without advanced technology. For example, the rocket technology that enables us to blast off from Earth is essential for taking scientific measurements in space. And then there's the discovery of X-ray technology. That breakthrough significantly advanced physics and opened up new areas of study, like atomic structure and spectral analysis. It's a perfect example of how science, engineering, and technology are interconnected, each one fueling the progress of the other. All of this shows how vital technology is in expanding our scientific capabilities and understanding the universe better.